Hello guys, welcome to today's video. So quickly I just want to show you how to do implicit differentiation, a new way of doing implicit differentiation, of course with our knowledge from partial differentiation. So let's dive in right away. So we are given this example to find dy dx for x cubed plus 3x squared y is equal to 3xy squared plus y cubed plus 5, and this is going to be a crash course, so it's going to be fast. We're not going to really emphasize on too much details. I'll assume that you already know the backgrounds of differentiation at this point. So let's quickly find dy dx for this particular example given to us. So let's dive in right away. Now we have x cubed plus 3x squared y is equal to 3xy squared plus y cubed plus 5. Now we want to obtain dy dx, so we are going to differentiate with respect to x. So differentiate true with respect to x. Now if you're differentiating true with respect to x, this is what you're going to get. Starting with this term, differentiating with respect to x, you get 3x squared. Is that okay? Now you move over to this term. So this term is actually a product term. It is a product term in the sense that we have 3x squared y. So y is a function of x implicitly. That is why these are called implicit functions. So y is a function of x implicitly. Y is a function of x implicitly. That is why we are going to apply product rule on any terms that are considered to be product terms. So product terms are mixtures of x and y. So anytime you see those terms, you apply what? Product rule on them. So I'm going to take 3x squared as my u, and I'm going to take y as my v. So I'm going to keep 3x squared and I'll differentiate y. Differentiating y, I'll have dy dx. Okay, differentiating y is not just dy dx, but it's actually 1 dy dx. If you want to find dy dx is actually dy times dy dx. So this is the full chain rule for obtaining dy dx. Okay, dy dx is dy times dy dx. So this is my u. Remember, my u is 3x squared and my v is what? Y. So I'll do u dv dx, then plus, I'll now put my v, which in this case is y, then du dx, giving me 6x. Okay, and it will be equal to you will now apply the same product rule because this is a product term. So take 3x as your u, so 3x, and you differentiate y squared. Remember, if you want to differentiate y squared with respect to x, you have to do dy first, then add the multiplier dy dx. So differentiating y squared, you do dy giving you 2y, then add your dy dx, plus you're now going to keep 3, you're now going to keep y squared, and you differentiate 3x, giving you 3. And when you differentiate y cube, sorry, let me bring it down. Differentiating y cube, you're going to get 3y squared dy dx. Of course, from this rule, dy first. The dy is 3y squared, and the multiplier is dy dx. When you differentiate 5, you get 0. So the next thing is you now collect the like terms. Is that not so? In the sense that all the terms having dy dx will be brought to one side of the equality, and all the terms without dy dx will be taken to the other side of the equality. So I'll have 3x squared dy dx minus, now this term is coming over to the left hand side. So when it crosses over, remember this is 3x and this is 2y. So I should have a 6xy dy dx. Okay, then this term is crossing over, so minus 3y squared dy dx is equal to, then this term I have 3y squared, then what else do I have? Okay, just 3y squared, then I now have minus 3x squared, and I have minus 6xy. okay, so this term and this term are crossing over, that's why they have a minus sign. So if you collect the like terms, what will you have? You have dy dx is, factoring out dy dx, I have 3x squared minus 6xy minus 3y squared is equal to 3y squared minus 3x squared minus 6xy. So if you divide through by the coefficient of dy dx is now going to be 3y squared minus 3x squared minus 6xy over 3x squared minus 6xy minus 3y squared. Is that okay? So this is our dy dx, and this is what we have. Okay, the terms don't cancel out. The terms don't cancel out. It's just stays like this. Okay, although it looks as if they wanted to cancel out, but it won't really cancel out. So let's see how to get this same answer using another method, and in a much more faster and accurate approach. So you now be asking yourself, is this the ideal method to get the dy dx given this particular equation, or is there some simpler method that we can use to get dy dx? Yes, there is a simpler method. So take note of this answer over here. So the question is x cubed plus 3x squared y is equal to 3xy squared plus y cubed plus 5. Now if you want to get dy dx in pretty much a very short way, first things first is to take everything to the left hand side. Okay, you're going to take everything to the left hand side, so LHS. So when you take everything to the left hand side, you have x cubed plus 3x squared y minus 3xy squared minus y cubed minus 5 equal to 0. Good, this is step 1. Then after taking everything to the left hand side, you can see now that you can actually call this your phi of x comma y, because this is a mixture of x y functions. Okay, this is a mixture of x and y functions. And remember the formula for dy dx. Dy dx was given to us as minus the partial derivative of phi with respect to x divided by the partial derivative of phi with respect to y. So this is the short formula for finding dy dx. So we are just going to apply it by saying dy dx is equal to minus partial derivative of phi with respect to x. So I'm going to scan through this equation. I'm going to differentiate it partially with respect to x. So what does it mean to differentiate a function partially with respect to x? When you're differentiating a function partially with respect to x, you're going to take every other variable in that function to be a constant. Okay, let me rephrase this statement. When you are differentiating a multivariable function partially with respect to one other variable called x, for instance, then you are going to see all other variables in that multivariable function as a constant apart from x. So you're treating the other variables as if they were constants, and you're just focusing on differentiating the one that you want to differentiate, which in this case is x. So it means that for this particular function, when I'm taking the partial derivative of phi with respect to x, I'm going to see and I'm going to treat y as if it were a constant. So all the rules that applies to differentiation of constants will apply in this case. Therefore, beginning with this term, differentiating it with respect to x, I'll have 3x squared. Okay, Then going over to this term, differentiating it with respect to x. Remember, y is a constant, so nothing will happen to it. So differentiate with respect to x, I'll get plus 6xy. Y is a constant, that is why nothing happened to it. Now when I differentiate this particular one with respect to x, y square is a constant too, and 3 is also a constant. So when you differentiate this particular x term, you're going to just be left with minus 3y squared. Is that okay? Then coming over to this term, when you differentiate it, y cube is a constant, so it goes out. When you differentiate 5, it goes out. Is that okay? So this is all about the numerator. Then divided by the partial derivative of phi of y with respect to y, partial derivative of phi with respect to y. That means in this time around, I'm going to treat other variables in the multivariable function as a constant apart from y. So x in this time around is a constant. When you differentiate x cubed, it cancels out, is 0. Now when you differentiate 3x squared y, 3 is a constant, x squared is a constant. So when you differentiate the y term, you're just left with what? 3x squared. Is that okay? 3x squared. Then when you come over to this term, 3x are both constants. Okay, 3 and x are both constants, so y is the only variable, y squared. So which, when you differentiate it, you should get 2y on a normal day, but the 2y will actually multiply this particular term and giving you 6xy. Okay, there's a minus sign, and when you differentiate this one, you're going to get what? 3y squared. When you differentiate 5, it cancels out, 0. So this becomes the expression for your what? Dy dx. So another way of writing this dy dx, another way of writing it is by what? Opening the brackets. So opening the brackets with this minus sign, I'll get 3y squared minus 6xy minus 3x squared over 3x squared minus 6xy minus 3y squared. So can you notice that this is just exactly the same thing we got? 3y squared minus 3x squared minus 6xy over 3x squared minus 6xy minus 3y squared, and this is exactly playing out in the denominator in this particular side and in this particular side. So you can pause the video and compare the answers. So which method will you rather want to stick with? If you understand partial derivative, trust me, you want to stick with this second method of finding our partial derivatives. Okay, so the answers are the same, pretty much the same. It's just that in the upper one, these two terms are kind of swapped. Okay, but as far as the sign is still there, the terms are the same. So this is about implicit and partial differentiation. So all other things I'm going to be doing, you're going to see it in the main solutions for exact equations when we are solving exact equations. Now do you know that this particular equation over here, just one more thing, I'll round up this video. There's a way I want to put this equation, and you are going to appreciate exact equations. Now that we've found the derivation of this particular term with respect to x, the dy dx, if we cross multiply, you get dy into 3x squared minus 6xy minus 3y squared is equal to minus 3x squared plus 6xy minus 3y squared dx. So if you rearrange this particular equation, you have 3, bringing the dx terms to the left hand side, you get 3x squared plus 6xy minus 3y squared dx plus 3x squared minus 6xy minus 3y squared dy equal to 0. Okay, so this equation, expressing it in this form, this is the differential equation for this particular implicit function over here. Okay, so this is the differential equation for this implicit function, and this is the modified form of the implicit function. And this modified form, what did you notice? We took every thing over to the left hand side and we left 0 on the right hand side. Okay, so this is the differential equation for this implicit function. This is the differential equation, and this looks like one of those m dx plus n dy that you've been seeing. So in this case, m will correspond to what? This over here, and n will correspond to what? This over here. Are we together? So this is about exact equations, and we can actually go ahead to test if this particular differential equation is exact. So how do we test? Do you still remember from the last video? To test for exactness, my should be equal to nx. So let's begin with my. My is partial derivative of m with respect to y, and remember, m is this particular term over here. Okay, m is this particular term over here, and if you choose this term over here very critically, this term is partial derivative of phi with respect to x, and this term is partial derivative of phi with respect to y. Okay, so what we want to do is we want to find my. My is differentiating this one partially with respect to y. And how do we do that? Of course, the rules of partial differentiation tells us that when you're differentiating with respect to y partially, treat every other variable as a constant for the time being, and let y be the only varying variable, if I will use it in that language. Then if we begin the differentiation with respect to y, 3x squared is a constant, so it cancels out. So 6xy, how do you differentiate it with respect to y? By knowing that 6x is a constant. So when you differentiate 6xy, you're just going to get 6x. Okay, then when you differentiate minus 3y squared with respect to y, you get minus 6y. So let's check nx to see if nx will be the same. So nx is partial derivative of n with respect to x, and this is our n over here. So we want to differentiate it partially with respect to what? X. With respect to x. So to differentiate it with respect to x partially, you're going to take what? Every term of y as a constant for the time being, and you're going to treat x as the varying variable. So when you differentiate 3x squared, you get 6x, and when you differentiate minus 6xy, now 6 is a constant, y is a constant, so in differentiating x it becomes 1. So what you now have is minus 6 times 1 times y, which is minus 6y, and when you differentiate 3y squared, it is 0, it cancels out. So at last we see that what? My is equal to what? Nx. So hence, and both of them are equal to 6x minus 6y, or 6 into x minus y. So hence, what? The equation above, which is this differential equation here, DE, is exact. Okay, so this is just an introduction to what we are going to be doing in exact equations, and this is an introduction or just a crash course on implicit differentiation, partial differentiation, and the introduction of the first parts of exact equations. So in the next video, we are going to see how to solve exact equations, and we are going to dive into examples. Okay, so sit back and let us begin by seeing ourselves in the next video. Thank you very much. Please like, subscribe, share, hit the notification button to stay updated on posts, and take good care of yourself. So bye, peace.